excited about this. Okay. So a derivative of a function is referred to as the slope of the tangent line, which we know. It's the rate of change. I got some new pens and they're really thin, so I'm not sure if I'm going to use them or not, but I'll start with them. Rate of change. So we're looking at, everything can be related as rates, and we're usually going to we're going to use ratios. And when I talk about ratios, I'm really talking about it as a fraction question, like 3/5 equals x over 12. Like we're going to look at I don't know if that's any fuzzier. I think I'm losing my mind, or maybe I need glasses, one of the two. But we're going to be looking at using a lot of ratios with this. So when we talk about related rate problems, just know that this is kind of a strategy that we're going to use. So the first type is rate of change in respects to time. So if quantity x changes with respects to time, then any general quantity y, so we're saying x is changing based on time, and y also depends on x, which also changes with time. So they're all kind of linked together.
So Ms. Callan, would you say that for the top question, x equals to 36 divided by 5?
Yes, yeah. So when y is related to x, the rate at which y changes is related to the rate that x changes at. These are called related rates. So all we're saying is that these two things are connected, so their rates have to be connected as they change. Okay, so if y equals f of x, then according to the chain rule, you're going to love this. We are differentiating y in respects to time. So we'd have to take the differentiation of y in respects to x, multiply it by the differentiation of x in respects to time. So it's creating this link between the two rates. So this gets a little bit complicated quickly, and I'm hoping that doing more examples will make my explanation a little bit better. So for example, when a balloon expands, its radius increases, right? Everybody would agree with that? Like we inflate a balloon, all of a sudden its radius, like if we're looking at a flat balloon, maybe its radius is like 3 centimeters. If we inflate it, it's maybe 10 centimeters now. The volume and surface area of the balloon are related to its radius. Therefore, the rate of change of the surface area and volume are connected to that change in the radius. So we can't change the radius without changing the surface area and the volume. So everything's kind of connected. We know the formula of the surface area of a sphere is 4 pi r squared. For a spherical balloon, because sometimes they're not always sphere, they're like oval shape, teardrop shape. If the radius changes as a function of time, the surface area also changes as a function of time. The rate of the surface area with respects to time can be determined by differentiating both sides of the surface area equation with respects to time. All right, so here we go. We're going to do some math here. So we're starting with the formula A equals 4 pi r squared. So we're going to differentiate both sides. And remember, we're differentiating in respects to time. So your denominator is always going to be dt, because that's what it's connected to. Both are changing over time.
Where on earth do we get time from this equation?
Because we're talking about how long it takes for the radius, like how long, what the rate, if the radius changes or the area changes, it's over a specific period of time. So those times have to be linked together between the two. So with knowing that, so we're going to differentiate the area in respects to time. So my denominator is going to have the dt in it. So now we're going to differentiate the right-hand side of the equation. So we're differentiating 4 pi r squared. And again, over time.
This just annoys me is that we can't change these. Like,
Right, yeah, you can't cancel them off. Because they mean something other than just a variable. It's like, it's an action item, right? Like,
you can't kill
Maybe
James
it's
Bond.
a function b itself is a function
Right, like it's like f of x, right? You can't like the f of the x doesn't cancel out.
Yeah.
So it's like the derivative of.
It's like f of 4 pi r square over f of t, something.
Exactly, right? So there, we just can't cancel them. But good point. We're going to differentiate this using our rules from D3. So way back in D3. So that is just a constant. The 4 pi, it's just a constant. So that comes up out front. I'm doing it in multiple steps. I'm kind of doing like way back in D3 when we were just learning the rules, just so we can remember. You do not have to show me that. So this is the weird part of this. I'm going to put this in brackets just so you can see it, and that's over dt. So what we differentiated it in respects to, what did we do all this differentiating to? We did it to r, so we have to say we differentiated r. So that dr kind of stays together and stays the same.
Wait, where did like the DR come from?
Okay, so that's what I was saying before. Like, you guys know how I got the 2r, right? Because I pulled the exponent down in front, reduced it by 1, so we got the 2r here. But the statement that we're making is that we differentiate, or sorry, we derivated, there we go. We did the derivative of in respects to r. So we have to state the variable that we have worked with.
Oh, so it's not like a y inverse?
It's like y prime. So
Like
dr
dy
is like,
over dt was
yeah,
y prime.
exactly. You might also see this written like this. And that's probably more likely that you'll see it like this. So what we've done is we've differentiated this in respects to r in relation to time. So this is a derivative with respects to time, not radius. So that it's very different how we deal with it, and sometimes that becomes a little odd. Now, if we were differentiating with respects to radius, so let me write this. It would have been so much easier, and this is kind of what we've worked on so far. It would have been so much easier if we differentiated in respects to radius, because radius is the variable that's in the equation. So that would have been nice and easy to deal with, but alas, we don't like easy, because that's not who we are.
Yeah.
So if we did the derivative, in respects to the, oh, that pink's really hard to see, sorry, let me grab a different color. In respects to radius, go dark blue. If we did that in respects to the radius, this is gonna be dA. So we're differentiating in respects to radius, and that would just simply be your rules. You wouldn't have to do you wouldn't have to add anything else. So if it was just in respects to radius, this is all we would have to do. But because we did this one in respects to time, because time affects all parts of it, This is where the dt on the bottom comes in. Oh my goodness, if one page took 10 minutes, that's not a good sign. Yep,
Like what if like a the function a is dependent on r.
right, yes.
So can we just write a prime equals to a?
You
pi
totally
r?
could. Yes, you could have written it as a prime equals 8 pi r, because a is, like, the radius is related to the area or the
Y
surface.
prime equals to 8 pi x.
Exactly. So this is old school, not old school, it's not that old. We've been doing this through the whole course. I would say that this lesson is kind of a, not a standalone lesson, it's related to everything we've done, but it's kind of like something we could pluck out, do it in isolation, and the majority of our course is just doing differentiating in respects to the variable that's in the equation. This is the one-off to show you how to do it when it's related to something else. So just know that this isn't everything, it's just kind of a one. All right, it's never good when you get a whole page to do the math. Just saying. Okay, given that two variables are functions with respects to time, so t of x and y of x, where x to the exponent 4 minus y to the exponent 4 equals 65, and we know that the derivative of y over the derivative of time, or derivative of y in respects to time, is equal to 3. We want to find the derivative of x in respects to time when x is equal to 2. You're like, holy Hannah, I don't know what that means. I don't know what that means, but that's okay. We're gonna get there. Oh, gotta do my grad memo. Just got my notification. All right, so we're gonna do the derivative of each side of that equation, right? So we're gonna do d of x to the exponent 4 over, what are we doing this in respects to? Time. So dt minus the derivative y to the exponent 4, the derivative of time equals, oops, got my letter D in front of there.
Wait, where did you get D65 from?
The equation,
Oh,
right? So we're breaking it down. All right, so we're going to derive everything just like our D3 rules. So this is going to be 4x cubed. Now, what letter did we derive here? X, right? So this is going to be multiplied by dx over dt. Everybody good with that? Because we're stating the fact we derived related to the variable x. This one, we're going to use the rules again. So 4y cubed. And then what did we relate it to?
Y. So we have dy divided by dt.
Yep. What's the derivative of 65? 0. What's 0 divided by dt?
0.
0. So, I mean, if you wanted to do this, you could, just to remind yourself if you wanted to do that. But really what we have, ooh, sorry, let's do my y first. I don't want to skip that step. You don't have to write it, but it is equal to 0. So this is the equation with respects to time. Now we know some stuff. What do we know?
dy over dt.
We know dy over d3. We know this has a value of 3. What else do we know? Y is equal to 2. So we can substitute in for the y. And now we're solving for, what are we solving for? The dx over d2. What would that, we'd have too many variables at the end. We'd have a dx over dt, and I want to say that you're not going to break those apart. They're kind of like stuck together. We're not solving for a single variable. We're not dividing out t. They get stuck together. So even if we subbed in all the information that we knew, we're still missing, we're trying to solve for this guy, so we need to know x in order to do it. We have too many variables at this point. How could we find x?
But 1 second, where do you get the 3 from?
Go right here in the dy over dt is equal to 3.
And 2, okay. and
Y equals 2, right? So right now, because I said this guy doesn't get pulled apart, that guy doesn't get pulled apart. So we have a variable of x, and then we have this dt or dx over dt that we need to find. So how we're going to find x? It's old school. Go back to the original, because we know y is 2.
X times x raised to the power 4 minus y raised to the power 4 equals 265. Then substitute y in there and get x.
Yeah, so exactly. So we're going to go x to the exponent 4 minus y to the exponent 4 equals 65. We're trying to find x when y is 2. Oops, sorry, that should just be a subtract sign. $16? And if we do the fourth root of both sides, yeah, it would be plus minus 3, just we don't know which one to use, right? Because when it's to the exponent 4, it could be a positive 3 or it could be a negative 3.
And then
So we have
you
both
try-
those answers.
Then you insert this 3 inside the 4x.
Exactly. So we're going to have to do it twice, though. Right? So we're going to do it, maybe I'll move over here for a second. Do the positive one first. So when x is 3. So I'm going back up to this line right here, like this one right here, and because I have all my stuff substituted in it. So 4 times positive 3 cubed times d of x over dt minus 4 times 8 times 3 equals 0. Having a hard time with my x's today.
Eight ninths.
8/9, I just pumped it into a decimal real quick. All right, so now we're going to do this whole thing again when x is equal to a negative 3. So we're repeating this. So we'll have, well, I could probably do this in my head.
Let's write it down.
Okay,
Sake of future viewers.
oh, I like that. This should still be a positive 3.
It's the same number.
It's a positive 3? No, it should be a positive 3 here. The reason why is because that 3 belongs to dy over, yeah, I made that mistake. So this should be a negative. Oh, that's a little messy. So we have 2 possible rates that would work, one positive, one negative. It's because we had those 2 possible answers. It's a little bit confusing for sure when it's related to time, which isn't in any part of the equation, which is kind of a pain in the butt. Okay. Okay. Knowing that the sides of a square are increasing at a rate of 4 centimeters per second, how fast is the area increasing at the instant when each of the sides of the square is 20 centimeters? Fun times. Okay, so we just need to define some stuff here before we can start using d of x, d of t, that sort of thing. So if we were to say side length, let side length equal x. And we're talking about area here. We want to know something about area. So let A equal area. And we have one more thing that we have to define.
The sides.
We did the sides. What's our rate in?
Time.
Time in seconds. So right away we know one thing. What do we know? We know dx over dt. The side length is increasing at a rate of 4 centimeters per 1 second. So the derivative of d of x over d of t equals 4, and we can write in centimeters per second if that probably, will we use the centimeters per second when we're calculating? No, that will be like final answer kind of thing. So what the question is asking is how fast is the area increasing? So what are we trying to find? Correct. We are trying to find dA over dt. Okay. So this has to do with area of a square. What's the formula for area of a square?
Side times length.
Side times length, but we know that all sides are the same, so side squared. And what do we say our variable was that we were using for the side length?
X, so X.
Okay, so area of the square is x squared. So we are going to differentiate both sides of this equation in respects to time.
Previously you told us that like for X, for like other letters we need the Y prime, but for X we don't need that. How come we need that?
Sorry, I didn't hear the last part of that.
Like, cause I know we learned from previous lessons that like when we have Y, then we put the Y prime, but when it's X, we don't need to worry about it. Because
we were differentiating in respects to x when we were doing, what was it, implicit differentiation?
Yeah.
What we were doing in D6?
Yeah, D6.
We were referring to that because X and Y were both in the equation. That's why we,
Oh.
is there a T in any of these equations?
No.
No, so we're adding in that third variable that's not related to the equation at all. That's why we have to do all this junk.
It's because dx over dx cancels out equals
Mhm.
1, so we just don't write it as a.
Exactly, yeah.
Yeah.
Okay, so we're gonna go ahead and we're gonna differentiate this. So dA over dt equals 2x. And what did we just differentiate? Dx over dt. Okay. Super easy, right? Guess you're like, no, not really. I don't know what you're talking about. So we know some things. It wants to know the rate when the side length is 20 centimeters. What does x represent? We defined it. It's the side length, right? So we can substitute in here 20 for the x. What do we know dx over dt is? We know it's 4.
So 2 times 20 times 4?
Mm-hmm. Sorry, I didn't realize my thing was there. So what are the units of measure on this?
Centimeter squared.
Centimeters squared per second. So we know as if sides of the square are increasing by 4 centimeters per second, we know that the area of the square will also increase at 160 centimeters squared per same second. So this is how we're connecting the two things together. Some people, oh, well, if that increases by 4, then the surface area has to, or the area has to increase by 4. It's not as simple as that. I wish it was, but it's not. Okay, so not too terrible, hopefully, question mark. Okay, do you guys want to try to set this up, or should we set it up together and then you guys do it, or do you want me just to keep rolling with it? How about we do the first one together? Okay, so we're going to define our variables. So a ripple tank, to do an experiment in physics, students set up a circular wave front that travels outward at a rate of 12 centimeters per second. So we're dealing with a circular wave. And it's not a sinusoidal one, it's have you ever seen like you throw a pebble in the water and it goes like the circles, right? So that's when it's talking about a circular wave, that's what it's talking about. What is the rate that the area inside the wave is increasing when the radius is 6, and then when the radius is 100 pi, and then when 5 seconds has elapsed? Okay, so let's just start with the first one because that's very overwhelming for all of those things to happen at once. So let's define our variables. What do we know? Okay, all right. What do we need when we're talking about area of a circle?
Radius?
Radius, so let's define that. What else do we need to know when we're talking about area? What's the other letter in that formula? No. What's the other letter? There's only one other letter on the left-hand side. So what's on the left-hand side? Area. So A equals area. There's one other thing that we need to define. Time. You guys are like, I don't know why we have to define these all the time. I guess technically we should always define our variables when we're using them. Like Rahat said, for future children watching this video, we'll give them all the letters.
So this, all you gotta do is just remember that.
You just gotta remember rat. Sure, I like it. If we're dealing in area of a circle. Last time it was that? Like, how would we pronounce the X? Because it was XAT. In Chinese, X's are like,
Sha.
are they Z's?
They're kind of like these.
Okay.
Yeah, it's like these.
It's like a Z. Okay, so obviously we're struggling with pronunciation of an X, but we'll work on it. Okay, what's our rate? What is our rate related to?
Time.
What's this one related to? Definitely time. What's the 12? If it's so, it's going to be the dr over dt is 12 centimeters per second. And you're like, okay, why isn't it the area? There's a couple of things. One, it's moving out at a linear, like it's a linear distance given. It's a centimeter, so I know it's going to be a radius or a side length or something like that. If it was centimeters squared, it would be area. So just kind of keep that in mind as well. Okay, so part A, we're talking about area. So area of a circle is pi r squared. And we're going to differentiate both sides.
What did they do to my boy?
Are you okay? No, Rahat, you're not okay? I'm randomly using brackets. I don't know why, but I've just decided I'm going to. So
But we know that the R is 6 centimeters,
we know the r is 6, and what do we know dr over dt is?
12 centimeters per second.
Right. Do you guys want to leave it in terms of pi, or do you want,
Let's murder the pi.
well, we can't, do you want to just leave it as pi, or do you want to do decimals? Leave it as a pi? Okay, so 12 times 12, I know that one in my head. 144 pi. And what's my units of measure on this?
Centimeters squared per second.
Yeah. Oh, sorry, I forgot the dt, thank you. So the area is increasing at a rate of 144 pi as the radius of the circle increases by 12 centimeters per second. Okay, B, when the area is 100 pi, oh, the squared should be up top, sorry, that bad font. Okay, so with this piece of information, my formula that I found right here is not super useful to me. Because if I put 100 pi in for the area and try to differentiate that, what would that give me? If I'm differentiating it, it's going to give me a 0. And then what am I going to have still on the other side? I know the dr over dt is 12. Do I know the radius? No, I do not. Can I find the radius? I can. So we said that area is equal to pi r squared, and we happily know that our area is 100 pi. I skipped some steps there. Why did this one I not use the plus minus? Where in the very first example I did use the plus minus. Radius is always going to be positive, and in the very first example, there was no context to that question. It was just simply letters, like it wasn't an area or distance or anything like that. So now that I know the radius, I can dump it back into this equation and find the rate. So dA over dt.
Wait.
Whoa.
Okay, so your area equals. Oh, okay. So our area equals 100 pi. Okay. I screwed up there big time.
But do you get it now?
Thanks, got it.
Okay, cool. So 2 was in here, and the radius we found was 10, and we know our rate is 12. And we're going to leave it in relation to pi. So I have 20 times 12 is 240 pi centimeters squared per second. Okay. C. After 5 seconds has elapsed.
So t is going to equal to 5.
We're looking for the rate, right? We're always looking for the rate of the radius. Okay, so this is where, and I'm not sure that this would pop out again. I'm always trying to find the radius, like, I need the radius to put into the equation. The rate's a little bit difficult to do. You could try to figure it out if I started at 0, my first second, how far have I gone? Like how,
0?
so I dropped the pebble in at 0. What's the first ripple after 1 second? 12. After 2 seconds?
24.
After 3 seconds?
48.
No, that's 36. You missed one.
Yeah,
So you see the like you could do it by hand or a
So
table of
5 is
values.
60.
There you go. 5 is 60. If you want to see the math behind that, we just would have done it as a ratio question again. So we have 12 centimeters for every second, and we want to know where it is after 5 seconds. So,
Oh, okay. So that's
Right.
an easy little kid problem.
right, so we know that that is 60 centimeters. Okay, oddly enough, 2 people in my family asked me to do rate related, like these kind of ratio questions in the past week. Like, I don't know what, like, I get these random text messages that ask me to do, I don't know, they needed to know the 60. And I was like, just do it as 2 fractions. No, they were, one person was figuring out the grams of sugar in yogurt or something like that. And they were like, they had the rate for the big container and they wanted to do anyway. So that's what I was doing for yogurt. Like, it's just weird, the things that come into my life.
You're just like the on-call math person.
You all will be those same people in your family's lives, just FYI. Hey, Miss Thompson,
Hey,
how's it going?
good. You? Miss Thompson, I saw you at Canadian Tire yesterday.
I did. I was buying light bulbs.
So that's gonna be your new radius. Can you guys do the rest of that? Figure it out?
No.
No, me either.
No mention from,
It's recording, just FYI.
oh, okay. No mention from. Okay. Oh,
And that's why I
okay.
sent you the form.
Yeah,
And I gave her the breakdown.
yeah, no.
No.
Yeah, no. Okay.
So she knew the pricing and I put it in my email.
Yeah,
The
okay.
base study price was 65,
Yeah.
the
Yeah,
name
yeah, yeah.
the short and hood was
Yeah. Well, she's here today.
Yeah.
In case of emergency.
So this question asked for the rate that the area was increasing in 3 unique different ways. One was straight up, here's my radius. The other one was find the radius from an area given. This one was find the radius after a time had elapsed. So all dealing with the rate of the area, but all asking for it using a different type of information.
All the variables we used.
All the variables, yes, exactly. All right, here we go. Oh, this is a long lesson. Oh my goodness. Okay, a ladder 7 meters long has been placed up against a wall. Not realizing the bottom of the ladder on a fairly smooth surface, the man started to climb the ladder. To his dismay, to his sadness, the bottom of the ladder slipped horizontally, so it's moving away from the wall at a rate of 0.75 meters per second. How fast of the top of the ladder is falling? So how fast is the ladder moving down the wall when the bottom is 5 meters from the wall? Holy Hannah. Okay. So let x equal horizontal distance. And I need one more variable. What's my last variable? Okay, what rate do we know? It's given right there in the pretty picture.
He's falling at 0.75 meters per second.
He's not falling, he's sliding out, right? So dx over dt is equal to 0.75 centimeters. Ooh, this should be centimeters. Yeah, that was a pretty fast fall if it was meters. Whew. Okay. What shape? Okay, because like this isn't an area question. This isn't anything to do with this. This is about like, I'll give you a hint. It's about height and width here. And what shape is being made with
Triangle?
a triangle? That's like you've gone back to grade 10 math again. I tell you, calculus, all you need is grade 10 math. You need a little bit more thinking than that. So if we want to know like what the height is here versus the length is here, what handy formula?
Pythagorean theorem?
Nice. What's wrong? Oh, okay. So why didn't I put c squared here? Like, because it's a squared plus b
Because we
squared.
already have that.
And what do we know is not going to change?
The hypotenuse?
We know the ladder distance isn't going to get shorter or longer. Like the ladder is 7 meters.
Unless he buys one of those like
Collapsible ones. He's got other problems then. He's got other problems. Okay, so we're going to differentiate both sides of the equation. In relation to time. Are you guys all okay that I just jumped to 0 there? We showed it in another one, so.
There's too many variables.
There's still too many variables, good point. Because we know what the x is, right? We know that the x is 5 meters from the wall, so we know x is 5. We know the rate is 0.75, so we know this one and we know this one. We're trying to solve for this one, I need the y.
Use the Pythagorean theorem, x squared plus y squared equals 249.
Exactly. So what we're looking for is when x is 5, what's y? So we're going to go back to y squared plus 5 squared. That should be 7 squared. I just got a little crazy there.
49 minus 25.
How much is that?
4, 24. 24. Square root of 24.
And I'm going to default to what? I'm going to go to positive because we're looking at a distance here. Again, it's related to the question. If I didn't have a context, I might use something different. So let's go ahead and fill in what we know. 2 times 5 times 0.75 plus 2 times root 24 dy over dt equals 0. I got too excited and I tried to move things. So dy over dt is going to be negative 0.75. And it's a negative number. And is that okay?
No.
Well, it's a rate. Rates can be negative. Which way am I falling?
Oh, yeah, down.
I'm going down. So a negative number in this case is okay because we're looking at a rate and it's just because it's going in a downward direction. It's not sliding up the wall, it's sliding down the wall. Okay, are these getting easier? Do they make kind of sense? No? Yes?
If we could require a lot of
Yeah, they do require a little bit of thinking.
This reminds me of like
you need to
Mr.
just get started once, like you need the initial push of the train,
Mhm.
the car.
I'm just wondering, we probably have time for one more. I think I'd like to do the last example with the streetlight. Example number on page 6 is really similar to stuff we've already done.
This reminds me of like Mr. Beck's baby books. Because chapter like this, chapter like 8,
Mm-hmm.
this was like so good for like 1, 2, 3, 4, 5, and I was just like, time for the move.
Okay. So, a 1.2 meter tall boy runs towards a lamppost at the rate of 2.2 meters per second. Ooh, look, we have a rate. That's exciting. The light bulb is hanging 4.2 meters above the ground. At what rate is the end of his shadow moving when he's 2.5 meters from the post? And what rate is the length of his shadow changing when he's 2.5 centimeters from the post? Okay, so let's talk about some things. This is his distance here. And then his shadow extends behind him because the light's in front of him. So his shadow will be behind him. Okay? So let x equal the distance, oops, that's supposed to be an O, from lamppost. I'm having a hard time spelling today. Okay, what's y?
The shadow.
The length of the shadow.
And then S is just going to equal to as x plus y, right?
Mm-hmm. So what is that?
Then of the end of the shadow from the lamppost.
Yeah, so let S equal the distance from, what if does lamppost have one? No, it has two. I'm only writing it with one. And length of shadow. I think what would have been easier if I just went X plus Y. That would have been, that would have been so much better. I've spelled lamppost wrong the whole time.
Late correction, but just a reminder to all girls, if they are having volleyball after school today, so volleyball club with Mr. Mullen and Ms. Rockenwagner today after school. Thank you.
Okay. Here we go. So what we don't know anything. We know nothing. Or do we know something? Do we know something?
We know how tall the dude is and how tall the street lamp is.
Okay, and we know one other thing. What else do we know? We know a rate. What's the rate?
Plus y squared.
Oh, the rate is 2.2 meters per second.
And what rate is that?
The how fast he's running towards the lamppost.
Kate, give it to me as a derivative.
dx over dt.
Dx over dt, because it's related to the distance from the lamppost. So dx over dt
And then
is
so
equal
by
to
the letter
2.2, we're going how fast? Meters per second. So in question A, what rate am I trying to find?
ds over dt.
Right, we're trying to find ds over dt. So for part A, we're looking for ds over dt. And part B,
So it's just dy over dt.
it's the dy. Yeah, we're doing the dy over dt. You know what, guys? I think I'm gonna
Call it a day.
I don't know. I think like I'm gonna cram it in here and it's not gonna fit. And then I'll be rushing through and I think we'll be too rushed. So what I'm gonna encourage you guys to do is I'm gonna stop the video here. We'll pick this up, like we will finish this one when we get back. Take a look at your D6 or your A6 assignment and get as much of it as you can done, because on the Tuesday we get back from break will be our